So we're now going to take a look at module 7, which is essentially all about light. So firstly, and obviously the models of light, including both its sort of particle and wave theories. So firstly, what is light? Is a question that has plagued scientists for, well, many centuries. And we'll need to kind of, in our module 7, we'll start by looking at Maxwell. Now, this kind of ties in with what we've said with electromagnetism. And basically, Maxwell looked at the electromagnetism equations. So we've got what's called Gauss's law. You've got Gauss's law for magnetism. You've got Faraday's law. You've got the Ampere-Maxwell law. Collectively, these are known as Maxwell's equations. And what he basically did was he basically took these 4 equations and recognized that as a result of these things, and we could write out all the laws, but I don't think you would particularly need to, and you always look at simplified versions of these laws anyway. But what he basically realized as a result of these equations is that if you have a change in the electric field, it will create a change in the magnetic field. And that's basically because your change in electric field will then generate a change in charges. It will accelerate, which will create a magnetic field, and that will change and so on. And as a result, we're saying that a change in the electric field will get a change to a magnetic field. But as you probably saw from electromagnetic induction already, that goes both ways, because a change in the magnetic field will generate a change in flux, and that change in flux will then, by Faraday's law, generate an EMF, which must result in a change in the electric field. So essentially, we're saying that because you've got these 4 equations, then the logical conclusion, putting them all together, and this is what Maxwell did, is he recognized that a change in electric field must generate a change in magnetic field, which must do this. And so therefore, it must just continue forever. And therefore, we can therefore think of this as an electromagnetic wave can be produced. In other words, if you make a change to an electric field in such a way, it will generate a change in the magnetic field, and that will then go back to a change in the electric field. But then this will cause a change to basically continue to propagate throughout space. And from year 11, that would essentially be a wave. And so Maxwell said, you must have a type of wave called an electromagnetic wave. And again, from the equations, these are all sort of electromagnetic theory, he calculated that V must equal 1 over the square root of mu naught and E naught. And basically, these are constants, all right? So mu naught, we kind of mentioned, is related to your magnetism. So it's the permittivity of free space. And your E naught is your, sorry, wrong way around. This is your permeability of free space, and this is your permittivity of free space. And basically, if you stop in the constants that we kind of know or have worked out, then we're basically saying this is roughly 3.0 times 10 to the 8 meters per second. So in other words, Maxwell's contribution is that he predicted, well, he unified. So if you're thinking about his sort of contributions, we're saying that he unified these 4 equations and came up with a prediction for electromagnetic waves. And he also predicted the speed of an electromagnetic wave. Okay. And that's basically what Maxwell did. All right. And so, well, I mean, we know nowadays, of course, that what we've got with your speed of light here matches our speed of light. And so that also kind of gave evidence for light being an electromagnetic wave, which, is definitely one of the theories. Now, of course, to see if speed of light travels this fast, we kind of need to, measure the speed of light. Now, I don't plan to go into this in great detail because this is one part that you could kind of very much sort of read. But I suppose what you need to understand is that speed is basically calculated by distance over time. Now, the problem with the speed of light, of course, is that the speed is very fast. So to do it meaningfully, you either need a very large distance or you need to have a very, very accurate timer, essentially. And, generally speaking, neither was really available. So you can think of your early measurements, all right? Your earlier measurements would be, for example, Galileo doing it on top of this hill, which, is woefully inadequate in terms of how far away it is, right? And then you can also then talk about Rome's sort of using ellipse periods of Io, which is Jupiter's moon. Okay. So you can then also talk about Bradley's. So Bradley sort of estimation using parallax. You don't need to know every single one of these, but this is just giving you ones that kind of you can look at. Okay. Then you've got the measurements with mirrors. So this is the rotating mirror. And this is basically with your sort of cogwheel. And so both of these basically are just trying to make it so that, yes, light's very fast. So how can we, they basically measure the time accurately, not with a timer because, that's just too hard, but basically we can measure the time, through calculations of how fast something spins and knowing like how the angle, right? So that's basically the concept there. And then, after that, you've got, ones based on interferometry. Okay. Now, it's important for you to understand that, and this relates into your relativity, but that the speed of light, as far as we understand nowadays, is constant. Right? That's our understanding due to relativity. It's one of Einstein's key things. And because the speed of light is constant, we now actually define to define our lengths. So how long is a meter? Well, 1 meter now is actually defined as exactly, how long light travels. So, I mean, if we're quoting the exact number, then we're saying C equals like, you can look this up, like 299,792,458 meters per second. And that's exact because now we're saying that 1 meter is 1 over 299,792,458 of the distance light travels in 1 second. So we are now saying that, well, light travels really fast, but this, you know, how fast does it travel? Well, this many meters per second, and a meter is now defined in terms of the speed of light. And that might get you to ask, okay, well, what's a second? And we've defined a second as well. And that's basically just a finite number of oscillations of a cesium, 133 atom. Okay. So this also allows us to be very much more precise with our definitions and with our measurements. Okay, so you can go and read those details. Okay, you will need to know them because you can be tested on them, but it's quite suited for you guys to read it. Now, you need to understand with spectroscopy, and this may also sort of help you with your chemistry in module 8. Basically, you've got different types of spectrum. You've got your continuous spectrum, and that will be typically sort of your black body. You can think of things from the sun, although technically it's more absorption spectrum. But, you've got your black body, you've got kind of what's called an absorption spectrum. And you've got emission spectrum. Now, so hopefully you guys understand the difference between them, okay? Between absorption, emission, continuous and more absorption and emission. And you need to kind of know what type of situations when you've got absorption, when you've got emission. So if we take a look at here, this will show you the sort of difference. So in terms of classification, you might get things that look like this, which is, that's continuous, so it's got everything. Emission, otherwise known as a line spectrum, is only going to have certain bits and pieces like this, and everything else is dark. Whereas your absorption spectrum is basically, something gets absorbed. So, your continuous spectrum minus this leaves you with your absorption. So that's your 3 different types. Now, when does that happen? Well, it kind of depends on the different scenarios, and you kind of need to know that. But if you imagine that you have something that gives out a continuous spectrum, then it will have all the colors without missing any. And if you imagine that this, spectrum then passes through something that absorbs only certain parts, and that's going to do with your sort of Bohr model of the atom, where, only certain energies are absorbed, right? And this, by the way, also relies, ties into AS for chemistry. But basically, if this only absorbs certain parts, then this is what's going to be left if you're sort of measuring over here. So this absorbed, and you're left with what's called an absorption spectrum. Whereas this one, if you're measuring what comes out of here, not what gets transmitted, but what comes out, this emits only these. And emits these because it's absorbed them at those energy levels, all right? So those are basically 3 differences of your different types there. And what you need to do after that is know sort of different situations where they're going to occur, really. So, if you have a discharge tube and recognize that's going to fall under sort of a line spectrum, so it's an emission spectrum. So, your fluorescent tube lights and so on are essentially discharge tubes. And they're going to actually, they might look white to you, but it's because your eyes basically, add everything together. So, discharge tubes include like neon lights, fluorescent, lights, and so on. And basically, that's going to be an emission spectrum. Okay, and we will consider, things like, we will generally consider these things to be continuous. So, sometimes they might not strictly, but we normally talk about sunlight that's reflected. We will often consider as continuous. Well, that's not strictly true in the sense that the outside of the sun also absorbs, so it's a little bit of a mix between continuous and absorption. But your sort of old style called incandescent light bulbs would also give off a continuous spectrum. And, you know, we're going to basically talk about sort of black body as well. Now, emission is also related to each element. So each element has particular atomic shells. They have a particular nucleus, which will then give you a certain, you know, and a certain atomic radius. So you can calculate the energy of each electron at each point. And for that reason, you can basically calculate the frequencies that they can basically all give off. So let's go. So you can see here on this sort of image, that's your continuous spectrum. These are not continuous. So these are, of course, you know, line spectrum. And if you are an element, right? If you're an element, then generally speaking, you can calculate specifically what wavelength these are. So these are kind of split by wavelengths. So that's long wavelength on the right and short wavelength on the left. And so basically, you guys have done, you know, your year 11 chemistry and module 8. So, and this directly ties into AS and AES. But basically, you understand that from things we'll cover, you know, later today and tomorrow, the energy is related to HF. So F is the frequency, but F can be counted as HC over lambda. So if you prefer wavelength, we can use HC over lambda. If you're comfortable with frequency, we can use frequency. So basically, for a particular, you know, energy level, you must have a particular frequency. And well, the energy level is going to simply be the energy, is the change in energy for the electron. And these energy levels relate to their shells, which relate to the number of protons in the nucleus, as well as the radius, so distance. And given that every single element will have a different number of protons, and the, you know, radius could often be different, then that means they'll have different energy levels, and so the change in energy will be different. And so basically the set of lines, which lines you get, will be different. And so we often simplify it to basically say that each element has like a, well, unique line spectra is what we say. But, you know, often this is sort of conceptually thought of as a fingerprint of an element. Okay. So because of what we said before about the element fingerprint, we can kind of use that information to basically find out, you know, what sort of elements we have. We use that on Earth, right, for AAS and AES, for those who do chemistry module 8. And we also use that, as far as our physics course goes, to basically find out more about our stars. And so, you know, you need to understand how we can use spectroscopy to, you know, understand things, to find out information, because clearly we can't send, I mean, it's just, you know, I mean, it's hard enough for us to get to the sun or Mars or things like that. I mean, we can send our probes to Mars. That's quite doable, even though it's expensive. And we recently have sent a probe to the sun, like towards the sun, recently in, you know, this decade, but, you know, something like last year or two, I think. But, you know, generally we haven't really been able to have anything that can withstand that sort of heat and radiation. So if you want to find more information about sort of stars and distant galaxies, you know, we just don't have the technology to do it, like as in to send a probe there. So, you know, stars or galaxies. But, you know, you find in your textbook that we say, hey, the universe is mainly made up of hydrogen and helium and all that sort of thing. So, you know, are we making those things up? Well, I mean, not really. We're not making it up, but rather, you know, this is as a result of, you know, analysis rather than sending a probe there. And we need to be able to figure out sort of the surface temperature of stars. And basically, just running through this very quickly, this will basically be applying black body radiation and assuming Wien's law. So we basically match the spectra with what we expect from a black body radiation, and we assume the star's a black body radiation. So we'll also need to basically be able to establish from this the rotational velocity of the star. We basically rely on the Doppler effect for that. And basically, we look at the sort of broadening of the absorption spectrum. Because basically, you know, if it's spinning faster, then the velocity on the left and the velocity on the right, there's a difference. And the bigger the difference, then the bigger the Doppler shift from year 11, it will shift the frequency that we see. And so it will start to absorb a bit more on the left and the right, as opposed to just strictly one line. It will start broadening out a bit. Okay. So we can also look at the velocity of the star. So not the rotational, but we can get the translational velocity. So the translational of the velocity is basically, you know, we can only get the radial component, not the tangential. And that component basically is determined by the blue or red shift. Usually a red shift because most stars are going away from us. But basically, we're trying to figure out, okay, so if a line is meant to be, you know, here, and it's now, we actually measure it here, then there's been a shift. And based on this shift, we can decide, okay, how fast is the star moving away from us to cause that shift? Okay. We can get the density of the star. Now the density is determined by basically figuring out the width of the spectral lines. And we can, of course, because we said we can work out the elements, then we can work out the sort of composition of the star by figuring out which line spectra have been absorbed. All right. And because if it's been absorbed, that means that thing must be there in the star on the way to you. And given it's been absorbed, that then means, of course, that it's there. And, you know, you've got the fingerprint. And that's essentially how you would sort of tell that aspect of stars. So I've covered that sort of relatively briefly, but hopefully it helps you sort of have an understanding of what's going on there. If you guys need a bit more detail on that, you can let me know in advance and can kind of do that for Friday. But hopefully this gives you enough background to kind of go back to your textbook to have a bit more of a understanding when you read it through again. Okay, so quickly we'll also get through the wave model of light, and then hopefully we can get to quantum photoelectric effect. So wave model, again, there are some bits that will kind of relatively go through relatively fast. The wave model of light essentially says that the light is an electromagnetic wave, and there are many things that support that. Because after all, we know that light reflects, we know light refracts, we also know that light can be polarized, we also know that light can diffract. And, you know, the fact that it can sort of polarize, diffract, and that ties in sort of to our interference, these strongly support wave theory. And, you know, of course, you've got Maxwell. But in terms of properties of light, it's really the diffraction, right, and the polarization that strongly pushed scientists to believe just before Einstein anyway, that light was a wave and that was it, right? So before quantum mechanics, there had already been lots of debate about, is light a wave or a particle? And, you know, you've got your, you know, differing theories between Newton's and, well, the Dutch guy, probably not pronounced correctly, but Huygens. And basically, because those, you know, one was a wave model and one was a particle model, and, you know, it had been going for hundreds of years. So it was really this polarization and diffraction that really settled it, until Einstein anyway, that light is a wave. And there's plenty of evidence that says, you know, in many cases, we can think of light as a wave, and that will sort of be good enough for our purposes. All right, and so we're going to focus here on diffraction. So diffraction of light is basically, you know, when light sort of spreads throughout a hole. So if you think of it as a wave, then basically if you've got a tiny slit, then what we're saying is if a wave was to pass, you know, let's say these were the wave fronts, we'll draw it in green. Now, if you've got wave fronts like so, then, you know, you'll get a tiny thing like this passing through and the rest is blocked. But what actually ends up happening is that it will then just sort of spread out this way. And so basically how much it diffracts is, in a sense, measured by this sort of diffraction angle. And that's very relevant to the wavelength. Now, you're not normally required to do too many calculations with diffraction, okay? But this idea that diffraction is related to the wavelength is part of the difficulty with light, is because if you're doing white light, well, it's got a whole bunch of wavelengths, and so you're not going to very clearly see diffraction. And if you're doing light of one color and one color only, I mean, you need to be really specific about the wavelength, because red light, you know, it could be made up of a whole bunch of wavelengths. But even if you were to get a laser and, you know, do diffraction, which would make it much more obvious, you also need to get a gap that's small enough. Because if the gap's not small enough, well, and you have to remember, light has a, you know, wavelength of a few hundred nanometers, so we're talking quite a small gap. Well then, as far as it's concerned, it's just a massive gap and it's just passed straight through. And so for that reason, because diffraction depends on wavelengths, and because, you know, light has a reasonably short wavelength, it took some time before scientists were able to, you know, observe diffraction. And so you need to understand basically the different models of light. And as far as diffraction goes, you need to basically calculate the fact that diffractions occur when d sine theta equals m lambda, and m is just an integer. So that basically allows you to calculate when the maximum and minimum, occur. So this is for the maximum. If you want the minimum, then it's m plus a half. So for maximum to occur, you calculate d sine theta equals m lambda, and for minimum, you'll have d sine theta equals m plus half lambda, for m is an integer. Okay. Okay, so now you also need to be aware of the different models we talked about. So we basically have Newton's model, which basically is a particle model of light. And we've got, you know, Huygens model, which is like a wave model of light, which sort of kind of predates, because you're talking hundreds of years ago, right? 1600s and so on. So, this is all before Maxwell. So Newton's particle model of light basically says light is made up of particles, all right? So basically he said that, he called it corpuscular theory of light. And basically he thought of light as made up of lots of particles. And, if you remember that, Newton did all his, laws of motion and so on. So he relied on basically, light to be well about, particles. And basically he was saying that there were particles that were moving, and, reflection can be explained by, a particle hitting and then bouncing off like a ball, right? And he also kind of explained sort of refraction incorrectly, but he explained refraction as, okay, so what happens is it's an interaction between sort of the material and the medium. And so it's going to speed up, according to him. And so it basically, speeds up the particle. And as a result of the speeding up the particle, then you actually end up, getting a, smaller sort of angle to the normal. And of course, that's not our current theory anymore, but that was Newton's theory, going back 400 years ago. And that allows us, to basically explain both reflection and reflection. Now, Newton expected the wave to speed up as, it refracts towards the normal. Now, Huygens, on the other hand, is a wave theory, which basically says that, each wavefront, each point on the wavefront acts as a wave source. So it's not really, anything groundbreaking for us, given that we've been doing this since year 11, how we draw waves and how, I drew. This is basically just using Huygens' principle, right? Every point is propagating out. But you could draw all the circles and so on, and this is basically the sum of all of those circles. It's the interference pattern of all of those circles. And, he would have explained reflection kind of like the law of reflection of waves, so nothing different there. Now, he would explain refraction as, well, the wave would slow down. And so that's one aspect where, well, when you do these, you can actually measure the velocity of a wave. And so that's one aspect where Newton's theory starts falling apart a bit. And that kind of gives you more evidence for Huygens. But as I mentioned before, it's really the polarization of waves and the diffraction of waves that really pushed, it was really polarization, which was later found, as well as the diffraction of light that strongly suggested that light was a wave. Certainly before, photoelectric effect and black body radiation. And so, what is polarization? Well, polarization is basically referring to how light, we're simplifying here, but we'll consider for transverse waves. And, transverse waves are often where we often draw a transverse wave like this. And we're just saying, okay, the particle goes up, down. And we're saying that's how they oscillate. But see, that's not really true, because in real life, your waves aren't necessarily oscillating up, down, you see? You might go, okay, well, they could do left, right, and they most certainly could. But no one ever said that your wave has to go up, down, or left, right. You could have a wave, and again, we're simplifying here, but we're just trying to give you an analogy. We can have a wave that, well, is not going up, down, is not going left, right, but it's kind of doing both. So it's going to be hard to draw. And I would recommend perhaps you could look at some diagrams in your textbooks or animations on the internet to help you sort of understand this. But basically, rather than strictly up, down, or in, out, it's kind of going on this sort of diagonal. So there's some sort of angle here. So what I'm basically saying is that in my example, it's going diagonally, all right? In my example here, my, thing is going diagonal. And you might go, well, diagonal, who cares? If I just change the axes, then it's just going up, down anyway. And you'd be right, which is why I'm saying I'm simplifying. So it's not trying to give you an analogy, but, the fact is if it's, going diagonal, then ignoring the rotation of the axes, because then you would be correct, you understand that, the particle is actually going along this axis as well as along this axis. And so we could conceptually polarize the wave by basically adding what's called a Polaroid. But conceptually, let me just, it's not really like this. It's only like this, you're kind of doing a rope. But basically, this is called a Polaroid. And the point is, after you go through this Polaroid, its light is now polarized. It's a polarized wave. So, if you imagine this is a rope moving rather than light, because light's a little bit different, although the concept is very similar. So what I'm basically saying is, as a result, I'm going to now basically take the vertical component only. In my example here, I can take the vertical component only. So I'm left with, the yellow part, which won't go as high. All right. Now, obviously, I could have done it the other way. I could have polarized it, this way. And that would then give me the horizontal component only. And that means, I suppose I shouldn't draw the up down at all. But in other words, I'm ending up with a wave that only goes, and it would still, the magnitude would still kind of, it will be relatively larger than the yellow, but it would still be, smaller than the green. Because you guys know from taking components that your component is always going to be smaller than your total, just the way it is. Okay, so that's basically what polarization is at a sort of conceptual level. If you've got a transverse wave with multiple components, you're only taking one component of it. And so, well, that's that. Now, light obviously is not quite like this, but the concept is still the same. So what you have with light is instead, it's actually oscillating in all directions. So this is unpolarized light. And when we put it through a Polaroid, then you'll end up only with one direction. So let's say it's kind of polarized in this way, hypothetically. And so you get polarized light after that. Now, if we now put this polarized light, which is, in the vertical direction, through another Polaroid, which, is in the left-right direction, then, well, we're basically taking the horizontal component of vertical light. So this is, polarized in the vertical, orientating in the vertical. This is Polaroid in the sort of horizontal. And it's probably quite clear to you, hopefully, that this will be no light. Ideally, no light, right? So things that you should probably note, that if you pass through a Polaroid from unpolarized. So unpolarized will become polarized in one direction, and your intensity will drop to half. Because basically, you're taking all the vertical components of all the waves, including all the diagonals. And so, when it's randomly split, it will just be half. And it doesn't really matter. If you did it horizontally, you would take the horizontal components of all of them, and again, it will be half. But more commonly tested, although you do need to know that. So, if it's polarized, and then you pass through a second Polaroid, then quite clearly, if it's in the same direction, then there's no change. If it's perpendicular, then no transmittance, nothing gets through, ideally. And if it's at an angle, then you use Malthus's law. So we're saying that the intensity that passes through is, well, how much was initially passed times cos squared theta. And you can see that when cosine of theta is 0, well, theta is 0, then of course the cosine is going to be 1, and so there's no difference. But if your cosine is 90, then it's going to be 0. And so basically we're saying that it's basically going to be proportional to the square of the cosine of the angle between the two Polaroids. All right. So now we'll move on to the quantum theory of light, which basically, is started off by black body radiation and, the Wien's law we kind of mentioned earlier. And we'll get to photoelectric effect. Now, we might need to go through photoelectric effect a bit more in detail tomorrow, because I know some of you are having trouble with that. But for now, for today, let me try to quickly run through both of these and see if that helps you revise for tonight. So we want to look at firstly at the black body effect, black body radiation. Now, black body radiation means you need to know what a black body is. And basically, it is an object that is a perfect, absorber. So it absorbs all incident. It absorbs all incident light. That probably better to write as that absorbs all incident light, or radiation for that matter. And so basically, it is a perfect absorber. It is also a perfect emitter. So something that people might not be familiar with, if you absorb energy well, like black, then you actually also emit energy more. So if you're colder, you'll absorb any more energy from the surroundings than white. But if you're hotter, you'll also cool down faster, which is why your kettle is not black. Your kettle is reflective, right? Because that's a poor emitter. So if you've got something hot, it doesn't emit very, much. All right, so that's your black body. Now, we are basically studying the radiation emitted by black bodies. And the problem, of course, is that when we were studying this, at the very end of the 19th century, they kind of went, well, we've basically had figured out everything about science, but there's just, a few problems left. Black body is one of them. And, well, photoelectric effect is the other. So what was the problem with black body radiation? Well, it kind of was the fact that you had this sort of thing. So the black body radiation, always had a peak. So, it always had a peak wavelength. As you heated up the black body, then we noted that, intensity increased for all wavelengths, which is not entirely a problem, but we also noticed that the peak wavelength became shorter. okay? And so basically, if this was t equals, 500, and if I'm saying that this is wavelength and this is intensity, and be careful with this. I mean, your typical graph does show, wavelength against intensity, but you could have graphs that give you frequency, which means, if I'm saying, wavelength goes down, then that means frequency goes up for electromagnetic waves. So, I'm going to draw a shift to the left, but if your horizontal axis is frequency, then it will shift to the right. So if this is, 1,500 Kelvin, say, then I could get something that looks like this. So this could be, 3,000 Kelvin. And so, I've got a peak as well. And the blue and the black never cross, and it's always above. And, there's been a shift to the left, right? Or, I could have a, T equals even lower, let's say 1,000 Kelvin. Yeah, I'm kind of making these up in terms of the curves, but the concept is the same. So note, because it's all black bodies, the radiation only depends on the temperature. Well, and the fact it's a black body. So once you take any black body, and because they're all perfect emitters, and you heat it up to a certain temperature, then they're going to emit all of the radiation that they have. And therefore, we examine the spectrum of that. And you'll notice that this is continuous because you don't have, okay, nothing, something, nothing. So this is a continuous spectrum. And so this basically is the problem that they were trying to solve. Well, that was the graph that they had got experimentally. And the problem was that it didn't match with classical physics. Because, see, here's your experiment result. But classical physics, using the theory we had then, says this, kind of. All right? So what we end up having is the fact that, well, classical theory predicts that as the wavelength goes down, the intensity will go towards infinity without limit. Now, we know that's wrong. I mean, for one thing, it doesn't match your experiment. But we also know it's wrong because, I mean, even though classical theory says that, we also know it's wrong just because, you can't have infinite energy, right? So basically, there's a problem with the theory. So, does it match experiment? But also, importantly, it also doesn't, it contradicts conservation of energy, right? You can't put in a certain amount of energy and get an infinite amount of energy. And we also had other problems that are sort of relatively more minor, but that is, it doesn't match the curve well. So even on the right-hand side, it doesn't match the curve well. So, I've kind of just freehand drew something that sort of matched quite well, but in reality, it doesn't match that like that. They had probably something that, oops, I'm drawing these freehand, but the point is, you don't need to know these details too much, but you had something that, something that was kind of like that. So it kind of matched well here, and you kind of had like another one like this. And it matched kind of well, sort of in the middle, but not so much there. So that matched well here. And so you had no theory that really matched everything, but you could kind of work around it and go, okay, we'll use this theory for here, we'll use that theory for there. But the real, big issue, of course, is that, well, you just had nothing that explained the left under classical theory. Now, you do need to be able to understand that you've got Wien's law. So Wien's law tells you that your maximum wavelength is equal to B over T, where B is a constant you can look up on your reference sheet. And you can quite quickly see, therefore, from this that as T goes up, lambda will go down. Okay. Now, basically, this was solved by Planck. So this problem was solved by Planck. Okay, Max Planck, who basically, had to, he was trying all sorts of, as was everyone else, trying all sorts of methods. And basically, the problem that he found was that he couldn't solve it, right? He was unable to solve it, no matter what. And so basically, he decided to try. It's kind of like if you're doing a math exam, you can't answer the question. And so you go, okay, I'll just try. I mean, I know it's wrong, but I'll try it out anyway and see what happens. And so what he did was he assumed that the energy was discrete. So for those of you who do, maths, you probably are quite comfortable with what discrete means under the new syllabus, because you have this, discrete part of your statistics. But basically what that means is that the energy level cannot be any level. So that, only, think of it like steps, right? So energy level, you can't have any level you like, but, only certain levels were allowed. For energy. So it's kind of like saying, okay, you can have one energy, you can have two, but you can have 1.5, which we kind of think is ridiculous because our experience of the world suggests that energy could be any sort of value. But if he assumed that it was discrete, then he would find that, and he assumes that E equals hf, where h is Planck's constant, and f is frequency. Then he found that he was able to actually mathematically derive the curve. He can match it. He can find an equation to, match this curve. He wasn't very happy with that, but he was happy that he was able to get the curve, but he's not happy with his assumption because he thinks that's ridiculous. And so this is essentially the start of quantum physics. Which, if you like, is, started accidentally by, and Planck is known as the father of quantum physics because he didn't like the idea, but he did it. And he did it to basically try to solve the problem. And he wasn't happy with how he did it, but it did solve the problem. And so while he wasn't happy with it, he managed to get the curve out. And so, after Planck, I guess people started thinking, well, it's just a mathematical trick, but how do we kind of, well, at least we get the right answer, so at least let's use it, right? And so, you'll need to read up a bit on black body radiation regarding the discrete energy levels, and also how, Planck assumed that, it was created by the oscillations of the particles inside the material. But basically, we've covered the key things that you need to know about black body radiation. That is, it's solved by Max Planck, that the energy levels are assumed to be discrete. In the explanation of the ultraviolet catastrophe, he's basically saying that the radiation is as a result of energy exchange between the particles which are oscillating and the field. And by basically using relatively high frequency and so forth, he was able to quantitatively, assuming that the energy equals hf is quantized, he was able to quantitatively derive this curve. And that essentially is, his main achievement. That, of course, had flow-on effects with regards to the photoelectric effect and, the rest of quantum mechanics, quantum physics, and then ultimately quantum mechanics. And that basically is the start of the process.
Hello.